Just let me know if you want to just say next, and I will move to next
Yeah,
page.
okay. Yeah, okay, fine. Sorry for the inconvenience. I like it wasn't working in my system. Okay,
Look forward to
so
ASP presentation. Yeah, let's start.
yeah, okay. Okay, fine. Yeah, okay. So I'm happy to present my work on cross-attention models for audiovisual dimensional emotion recognition. Um, so I hope this presentation will be useful for you and you can learn some new things. Next. So this will be the outline of my talk. First, I'll briefly introduce what is dimensional emotion recognition. And next, and then I'll present 4 variants of cross-attention models, and I'll go one by one, and what is the differences and what is the motivation behind each of these models. And then finally, I'll present some future research directions with like like in case if you're interested, maybe you can explore some of those directions. And next. And next. Yeah, so dimensional emotion recognition is the problem of estimating the continuous regression values of emotion in the two-dimensional space of valence and arousal. Valence is basically the range of emotions from being very sad to very happy. So as you can see in this figure, valence spans the range of emotions from being extremely negative to extremely happy. And similarly, arousal is the range of emotions where you can see from extremely very low energy to extremely highly excited. So as you can see, from calm, relaxed, content, happy to all the way up to tense and excited. So basically it shows the intensity of emotions, and valence shows the continuous range of all the emotions that we can express uh, with our face and voice. Next. Next. Yeah, next. Yeah, next. Yeah, so audio and visual channels, they are predominantly they are explored for emotion recognition in the literature due to the close relationship between facial and vocal expressions, and face and voice often exhibits several complex dynamic relationships within each other. And one of the most explored relationships among face and voice is the complementary relationship. um, uh, so uh, what I mean by complementary relationship is basically, let's say you have two source of informations. One is from face and one is from voice, and they convey these same information about the emotion being expressed, but they contribute to diverse information which is different from each other, and yet they complement well each other. So in this work, the main idea is how can we able to fuse the facial and vocal expressions uh, in order to make the best use of each of these modalities, and to have an accurate prediction of valence and arousal. So uh, and, next slide. Yeah, so in this, yeah, so in this one, it is mostly about fusing face and voice. Now if you look at some of the challenges in fusing face and voice, the first one is to effectively extract the efficient audio visual feature representations, because as I mentioned before, that audio and visual modalities, they exhibit complex relationship. So how can we able to extract efficient audiovisual feature representations that can take best out of each modalities? And then how can we able to effectively capture the complementary relationship across the modalities? And another challenge is we can be able to see wide range of variations in face and voice. For example, in face, we can have different challenges like pose, low illumination, or blur, and things like that. And similarly, if you take in voice, you can have some interference from background or some background noise, and that will mitigate the contribution of the emotion relevant expressions in face or in voice. And another challenge is how do we deal with missing modalities? So let's say if one of the modalities is missing, then how do we handle those uh, uh, those type of scenarios and still able to get best out of each modalities? Next. So the motivation behind this work is uh, most of the works prior to 2021, they focused on modeling the intramodal relationships, either using attention models or using LSTMs. Uh, and now you can see a lot of the papers on cross attention, but back then, before early 2021, not much papers are there. Uh, they try to explore the cross-modal interactions across face and voice. So as I mentioned before, back then, not many papers were there that were exploring the intermodal relationships across the face and voice. So in this work, the main motivation is to explore this research question: how can we able to effectively capture the semantic relevance of the intermodal complementary relationships across face and voice? Next. So
So
yeah,
I have a question. What
yeah.
do you mean by intramodal when you say intramodal relationship?
Yeah. So in videos, you have a temporal relationship, right? Which means
Okay.
uh, how the information is being affected over time. Okay. So intramodal relationship is basically modeling uh, the temporal relationships within the same modality. So that is called
Okay.
intramodal relationship. And when I say intermodal relationships, we try to model the temporal relationship across the modality. So which means that how the temporal relationship of one modality is affecting the temporal sequence of other modality, and what kind of interactions do they have, and what kind of information do we have across the modalities temporally. So that's what I call as intermodal relationship.
Okay. Nice.
Is it clear?
Yeah, yeah, yeah.
Okay, good. Okay. So yeah, so this is the first paper that I worked on this work, which is cross-attentional audiovisual fusion for dimensional emotion recognition, and this was published in FG 2021, and it was also selected as one of the best reviewed papers in that year. Next. Yeah. So this is the high level block diagram where given the video sequence, we try to separate the visual and audio streams, and then we have the visual clips, and we have the corresponding audio sequence. And for each audio sequence, we extract these spectrograms, which represents the corresponding video clip of the face, and then we feed that to the feature extractors for both visual and audio modalities to get the feature representations. And then once we get the audio and visual feature representations, we feed that to the fusion block, which is the a main contribution of this work, which is cross-attentional audiovisual fusion. And I'll go through this block in detail. And then once we get the attended features, we concatenate the features, and then we feed that to fully connected layers uh, uh, for predicting valence and arousal. And next slide. Yeah. So in this work, like we have used I3D network, which is predominantly used for action recognition in literature. And so we do pre-processing, we detect the face, and we do alignment on the faces, and then we extract the faces of the clips, and then we feed that to the I3D network, and then we get the feature representation for that corresponding video clip. And this is one of the models which is able to effectively capture the spatiotemporal relationships. So we used this model in our work. Next. Yeah, and for audio feature representation, we extract the spectrogram of the corresponding video clip, and then we feed that to 2D CNN model, which is Resonate 18. We tried different architectures, and Resonate 18 is one of them. And then we get the audio feature representation from there. Next. So this is the main contribution of this work. So once we obtained the visual and audio feature representations, we feed that to the fusion block. So in the fusion block, basically the idea is to compute the semantic relevance across the modalities based on the correlation, cross correlation across the modalities, and based on that we compute the attention weights, and then we use those attention weights to attend to the feature representations of individual modalities, and then finally we obtain the attended features. Like I'll go through that in detail in the next slide. Next slide. Yeah, so this is how we compute the cross correlation across the audio and visual modalities. So we have the matrix of XM, which is the feature representations of the audio modality, and then XV, which represents the feature representations of visual modality. So and then we compute the cross correlation across the feature representations of these two modalities, where we use weight matrices in between to deal with the heterogeneity across the modalities. And then once we get the Z matrix, which I call it as affinity matrix, because that gives you the relationship or how the feature representation of each modality is related to the feature representations of other modality across time. So once we get this affinity matrix, which is Z, and next slide. Yeah, so then we use this cross correlation matrix to compute the cross attention weights for audio and visual modalities, as we can see in these equations, which is basically we are applying softmax uh, on this affinity matrix, and then we get the cross attention weights. So these cross attention weights basically gives you the semantic measure of relevance of each feature representation of each modality across the feature representations of other modality. So to give you some intuition, what this matrix mean is, if you look at this matrix, we can see that each element of this matrix is basically dot product of the feature representation of one modality and the feature representations of other modality. So dot product will give you how similar those two feature representations are, right? So we make use of that information to compute the semantic relevance across the modalities. And next slide. And then once you get the cross attention weights, we apply those attention weights to the feature representations of the individual modalities to get the cross attended features. And we also we use skip connection here, which is residual connection, to retain the modality specific characteristics, because when we do cross attention, we may often lose some of the modality relevant information. So to retain that modality specific characteristics, we add the feature representations of the original features and the cross attended features, and then we feed that to the activation function, which is tan h here. That will give us the final cross attended features. Next slide. And this work has been evaluated on two datasets. Uh, no, in this work it is evaluated on RECOLA dataset. RECOLA dataset is predominantly used for challenges in ABEC 2015 and 2016. It has 9 videos, and each video is 5 minutes duration, 9 for training and 9 for validation. And then we use the concordance, the correlation coefficient as evaluation metric, which has been predominantly used in the literature of continuous regression because it gives you more accurate measure of how two continuous signals are related to each other. And then for loss function, we again use the CCC based loss function, uh, which is also mostly explored in literature in this for this problem. Next, we did some ablation study to compare this cross attention with some of the widely existing fusion strategies, and also we tried with some different architectures as well. So for visual, we tried 2D CNN as well as 3D CNN, which is I3D model. And some of the fusion strategies are feature concatenation, which has been widely used in literature. And then we also tried LSTM based fusion, which is another widely explored fusion strategy for this problem. And then we also did some experiment with self attention and finally with the cross attention. Next slide. So we can see that cross attention we are able to achieve the best result. We can see self attention is relatively better than feature concatenation and LSTM, but cross attention is even better than self attention. Next slide. So we did some comparison with state of the art. These are some of the prior works, and most of these works used LSTM as for fusion. And next slide. And we can see that we are able to achieve best results using cross attention when compared to the existing state of the art models. Next. We also try to visualize the predictions to better understand the model performance. So we can see here that that initially, we have some pose variations, uh, and slowly we have some frontal face. Again, we have some extreme pose variations. And but if you look at the predictions, we are able to closely track the ground truth, especially for valence. If you look at maybe I think after the 3,900 to 4,000, that you have a small spike in the ground truth. We are still able to track that spike in the predictions as well. Uh, yeah, and likewise for arousal also. Next. So yeah, so so though we are able to achieve some good performance with this model, some of the limitations of this approach is this cross-attentional fusion relies only on the inter-modal temporal relationships. So it doesn't take into account the intra-modal temporal relationships. So and most of the prior approaches, as I discussed before, that they rely on intramodal relationships using LSTMs or some attention models. So to further extend this work, we sort of like investigate the research problem that whether we can be able uh, to leverage both intra and intermodal relationships into this cross-attentional framework. And next. So this is the extension of the previous work where we tried to address this problem of how can we introduce the intramodal relationships in addition to intermodal relationships into this framework of cross-attentional fusion. Um, and this, yeah. And next. Yeah, so again, this is the high level block diagram. I won't go into the details of the feature extraction. It is pretty much the same, and I'd like to focus more on the fusion block. Next slide. Yeah, so this is the fusion block. So we have the feature representations of the individual modalities, which is audio and visual. So if you observe this block diagram, in addition to the feature representations of individual modalities, we also have the concatenated feature representations of audio and visual modalities, which we feed there to the cross-attentional framework. So the main difference of this work, the main extension is in the previous work, we compute uh, the cross correlation across the modalities, right? But here in this work, we compute cross correlation across the joint feature representation of the modalities, which is basically the concatenated version of the modalities. So I'll go through that in detail. Next slide. Yeah, okay. So okay, so this is the main difference here. So if you see the same affinity matrix, so this equation is quite similar to the previous equation that we saw in the previous model. But the main difference is in the previous model, we are computing the cross correlation across the modalities. But in this work, as you can see that we compute the cross correlation of each of uh, the feature representations of the individual modalities across the joint feature representation. So the joint feature representation, which is basically the concatenated version of the audio and visual modalities, it has both modalities. So by computing uh, the correlation across the joint feature representation, we are able to capture both uh, intra and intermodal relationships. So that is the main advantage of this model. Next one, next slide. Yeah, so here, so once we compute the affinity matrix, which is the cross correlation of the individual modalities across the joint feature representation, and once we compute that, so again, we add that to the feature representations of the original feature representations of each of the individual modalities. And then once we get the attended features, we use that attended features to get the uh, final attended feature maps of both audio and visual feature representations, as we can see in these equations here. And next, so in this work, we evaluated this model on two data sets, which is RECOLA and FOIL2. And FOIL2 is one of the largest data set, which has been widely used in conducting challenges with CVPR and ACCV. And this one has 564 videos from 455 subjects, and the annotations of valence and arousal will be between -1 to 1. And next slide. Next. Okay, so here we have used R3D model, which is pre-trained on Kinetics 400 dataset, which is an action recognition dataset. And then we fine-tuned on top of that. And then for audio, we used Resonate 18. And for loss function, we used the same CCC basic loss function as we saw in the previous work. Next. Uh, and we did some ablation study to better understand the performance of this model. So in this work also we did some experiments by trying different architectures as well as different fusion strategies. So we can see that joint cross attention, like I would say, uh, it significantly improved for valence, but though not much for arousal. Uh, but overall, it showed improvement for both valence and arousal than the previous cross attention model. And then we compared with some of the existing state-of-the-art models uh, on a FOIL2 dataset. So here we can see it on both datasets, on RECOLA and FOIL2. In both datasets, we are able to consistently improve the performance for both valence and arousal in both the datasets. Next slide. Yeah, and uh, please note that most of the existing models they use like attention models that rely only on the intramodal relationships or LSTMs, and this is one of the few works which try to focus mostly on capturing both intra and intermodal relationships and thereby showing better performance than existing state-of-the-art models. Next. So to better understand the performance of the model, I try to visualize the attention weights, which is basically, as we saw in the previous equations, the cross correlation across uh, the individual modalities and the joint feature representation. So we can see here, let's say, if you look at the face, maybe between 6 to 8, the person is having intense facial expression. Though it is not well captured in cross attention, it is we are able to get very high attention for that region with joint cross attention. Uh, and one of the reasons is, as I mentioned before, that in cross attention, like it focuses only on the intermodal relationships. But in joint cross attention, though we don't have information in one of the modalities, since we do the correlation across the joint feature representation, we are able to still retain the emotion relevant expressions in both the modalities. And these are the predictions of valence and arousal for both the cross attention and joint cross attention. And we can see that though cross attention is giving good performance, uh, joint cross attention is able to closely track the ground truth better than the naive cross attention model. Next. Okay, so in this work, though we are able to introduce both intra and intermodal relationships into this cross-attentional framework, uh, we uh, we further we sort of we explored the problem whether we can be able to further enhance the temporal modeling of both intra and intermodal relationships. Next slide. So till now, is that okay? Or if you have any questions, you can ask me before we go further.
We can ask. I have a few questions, but we can first finalize.
Yeah, okay.
That.
We can do it at the end. Okay, great. Okay. So so this is a further extension of the previous work, where in this work we we further improved the temporal modeling of intra and intermodal relationships across audio and visual for emotion recognition, which got accepted in ICAST for 2023. Next. So I'll be focusing mostly on the fusion model. And so we go next. Next slide. Yeah. Okay. So this is the fusion block. so so the main difference between the previous model and this model is, as we see that we introduced like LSTMs to improve the temporal modeling of the individual modalities as well as the multimodal feature representation. And and another important significant contribution of this work is to introduce the recursive mechanism. So as you see here, we introduced a recursive mechanism where the attended features are again fed as input to the fusion block to further refine the feature representations. And we go through that in detail in the next slides. And next. Okay. So these are the equations which we saw before. It is pretty much the same. Joint cross attention fusion model. and then we get the attended feature maps, which is the same as before. And next slide. Yeah. So the main contribution of this work is we sort of introduced a recursive fusion, which means that once we get the attended features, we again feed that attended features again as again as input to the fusion model. So by recursively fusing the features, we are able to obtain more refined feature representations, uh, which we do that as we see in these equations. And and in addition to that, like as we saw in the block diagram, we introduce LSTM as well. So by introducing LSTM, we are able to further improve the temporal modeling of both intra and intermodal relationships. And next. Yeah, next. Yeah, so we did some ablation study to understand the impact of recursion. So uh, as we can see that we did some experiments without LSTMs. The first experiment is basically the same as the previous work, which is the uh, joint cross-attention model. So and then we introduced LSTMs for both for improving the temporal modeling of both individual modalities and as well as the multimodal feature representation, which is audiovisual feature representation here. And we can see that by increasing the number of recursions, for two recursions, we are able to get the best performance. And and as we increase the number of recursions, we can see that um, the performance is dropping. So this can be attributed to the fact that as we increase the number of recursions, um, we are introducing more parameters, right? So that ends up in uh, like in overfitting, and so we are getting low performance after two iterations. And next.
There is an echo from the lab. If you can mute the laptop, if no one is like.
Yeah, next. Okay, so yeah, so this is the result in comparison with the previous models. So a simple feature concatenation and leader follower attention is one of the best fusion model which has been introduced in one of the challenges. And then we compared with the cross attention as well as joint cross attention. So we can see by introducing recursive fusion and as well as these LSTM uh, like modules, we are able to further improve the performance from 0.657 to 721. Like in both valence and arousal, we are able to get significant improvements. Next slide. Yeah. So so far we have seen different variants of the cross attention models that we have explored in trying to model the intra and intermodal relationships for emotion recognition. And one of the major limitations of all these models is most of these models assume that the modalities always exhibit strong complementary relationships. But in reality, we may not always have the strong complementary relationships. We can also have weak complementary relationships. So I'll go through that in detail. I'll explain what is strong complementary and weak complementary to better understand that. And yeah, so this is the next work. So in this work, we try to address the problem of weak complementary relationships, which is often overlooked in the previous models. And this work is the and this is a recent work which got published in ICME conference. Next. So yeah, so the main motivation of this work is as we can see from this figure. In the top figure, we have the facial and vocal expressions with very intense emotions, right? And we also have the frontal face of the person, which is which is good to capture the emotion relevant expressions. So since we have a very strong emotion relevant information in both face and voice, and they complement each other. If you look at the cross attention scores, they are very high for both audio and visual. But if you look at the below figure, where if you look at the facial image, you have extreme pose and blur and low illumination, and you have different challenges of the face. So in this for this one, though we have uh, strong emotion relevant expressions in voice, because of the poor uh, because of the noise due to blur and illumination, we can see that the cross attention weights is low for both the face and voice. So we want to address this problem, uh, and how we can be able to retain the benefits of strong complementary relationships using the cross attention model, while still being robust to handle scenarios like weak complementary relationships, as we can see in this bottom figure. And next slide. Okay, so in this work, we propose dynamic cross attention, where we have face and voice, and we get the feature representations. And then, if you see the fusion block, so basically, we introduced two gating mechanism here, one for each modality: visual gating layer and audio gating layer. And the objective of these gating layers is to provide an additional path for the original feature representations, and to bypass the cross-attended features in cases of weak complementary relationships. So we go through that in detail in the next slides. So this is how we do that. So in dynamic cross attention, once we get the attended features, which is basically the cross attended features, we feed that cross attended features to the individual gating layers. So these gating layers are nothing but fully connected layers, and which has two output units. And uh, and these gating layers will give you the importance of the cross-attended features and the original features. So basically, if you see the scores of this gating layer, that will give you the weights of to attend to the cross-attended features and the original features. And once we get that, we apply softmax on top of it to have probabilistic attention scores for uh, 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 the original features and cross-attended features. And next slide. And then we multiply those weights with the attended features as well as the original features. So these gating attention weights will control uh, the flow of information from the original features as well as uh, uh, the cross-attended features. So which means that the intuition here is, when the modalities are exhibiting strong complementary relationships, so we assume that these gating weights is supposed to give very high attention to the cross-attended features. And let's say if the modalities are exhibiting weak complementary relationships, in that case, these gating weights has to give more importance to the original features. So that way, we won't mitigate the impact of one modality on the other one. So that is how we obtain the gating attended features. Next slide. And then once we get the final attended features, we feed that to fully connected layers to get the final prediction. So we did an ablation study to understand the impact of this dynamic cross attention model. And this dynamic cross attention model is kind of plug and play. You can use it for any cross attention based model. And so in this work, we used four variants, but we can use it for any variant of cross attention model. So the four variants are a simple cross-attention model, like which is the first model, and then transformer-based cross-attention, and joint cross-attention, and recursive joint cross-attention. So by introducing this dynamic cross-attention to each of these cross-attention models, we can see that we are able to achieve uh, like improvement in all the cases, like especially for cross-attention and transformer based cross-attention, we achieved more improvement than joint cross-attention and recursive joint cross-attention. This is due to the fact that when the model relies only on the cross-model relationships, this dynamic cross-attention adds more value. But in joint cross-attention and recursive joint cross-attention, we deploy both intra and intermodal relationships, right? So that is why the improvement is less when compared to cross-attention and transformer-based cross-attention. Next slide. And yeah, so we compared with the state of the art models as well as the previous models, and as we can see that we are able to achieve the best result with dynamic cross attention on the top performing cross attention model, which is recursive joint cross attention. So yeah, so as we can see here in the test set, that we are not able to achieve the best performance, and the reason is in this model we don't use any sophisticated backbones, but in most of these existing models which has been submitted for the challenges, they use multiple backbones and ensembling based methods, and in addition to that they also use pre-training on multiple data sets to improve the generalization ability. So if we can incorporate those things into our framework, probably we can also be able to achieve better result for the test set also. Next. Okay, so yeah, so these are some of the qualitative analysis that we try to visualize the gating scores as well as the cross attention scores to kind of better understand the model. We can see here that uh, when we have a very high cross attention scores, then that means that the modalities are exhibiting strong complementary relationships, right? So in that case, we expect the gating score to give very high importance to those modalities, to the cross-attended features. So in the top figure, as we can see, when the cross-attention scores are high, we also have a very high gating scores for the cross-attended features. And in the bottom figure, we can see that when the cross-attended scores are low, which means the modalities are exhibiting weak complementary relationships, then we can see the gating scores are low for the cross-attended features. So which means that it is giving more importance to the original features. That way, uh, we don't mitigate the performance of the features by retaining the original features. And next. Yeah, and so here we try to visualize the predictions of all the models of whatever we did our experiments with, and we can see that uh, the one with the dynamic cross attention, which is RGCA plus DCA, which is the blue line, is able to closely track the ground truth better than the other ones. Especially, for example, if you look at the frames between 2600 to 3000 for valence, uh, we can see that we can see some spikes in the ground truth. The other cross attention models is not able to uh, track that one, but with dynamic cross attention we are able to track those spikes in the ground truth. um, Yeah, so and we can also see the facial images here that it is extremely blurred and extreme pose variations and a lot of other challenges are there. Next. Okay, so in conclusion, so in this, so in, the main motivation in all these variants of cross-attention models that we can see that that audio and visual modalities exhibit a lot of complex intricate relationship between each other. So which means that, like, you have a lot of heterogeneity, like where in some cases the modalities may complement each other, in some cases the modalities may conflict with each other, and they also have redundancy between each other, and they also have diverse information across each other. So it has a lot of complex relationships between these modalities. So trying to model these complex relationships across audio and visual modalities has been one of the promising research directions. And uh, and in this work we have extensively explored the cross-modal relationships, mostly the complementary relationships across the modalities, which seems to improve the performance. But also there is a lot more other issues with this, like for example, like missing modality, or for example noisy modality, or for example uh, um like the one that which we just saw, like the conflicting modalities, where the modalities may not agree with each other. uh, and also, like another issue with some of these models is the quadratic, the computational, uh, the cost of the cross attention model, because it is difficult to deploy these models on large scale data sets, because it takes intense computational support because of the computations in the cross attention module. And some more directions will be to explore this with additional data sets. As I mentioned before, that most of the existing works which has been submitted in challenges, they explore additional data sets to achieve better generalization of the model. So those can be explored. Next slide. Yeah, just to give you some of the future research directions that can be further explored. so, um, so one of the promising lines of research is to explore these weak complementary relationships, which is not much explored in the literature for emotion recognition. Um, um, so there could be better ways of dealing with these weak complementary relationships than dynamic cross attention. So that is one potential research problem that can be explored. And another problem, as I mentioned before, that the computational, the cost involved in the cross attention module. So how can we able to deal with that extensive the computational overhead, like using the parameter efficient models? And in fact, like recently I did some experiments with vision transformers, and which got accepted in URIP's workshop. And uh, and another potential research problem would be to deal with missing modalities and low data regime. Missing modalities is another challenging problem in multimodal learning, uh, uh, because it is often very difficult to deal with missing modality when you only have one modality, and especially in low data regime, which means that usually for emotion recognition it is very difficult to obtain annotations. So often we have to deal with the problem of limited annotations or limited data sets for emotion recognition. And also another potential research direction could be to explore this masked autoencoders, which is getting a lot of attention recently, uh, where we try to leverage self-supervised large-scale pre-trained models using masked autoencoders to capture the intricate relationships across audio and visual modalities. So yeah, so these are some of the directions that can be explored further. Next. Yeah, so thank you so much for your attention. And if you have some questions or if you want to discuss, feel free to ask me questions or we can discuss further. I hope I didn't take more time. So,
No, you are fine, I think.
okay,
1 hour, like one time.
okay,
Guys in
good.
the lab, we can't hear you.
Can we see his face? Like, yeah.
Yeah.
No. So here we have several questions. And thanks again, Praveen. So
Yeah.
nice presentation, except the title. I didn't like
Uh,
why you made a AS. I don't get it. You need to
can
explain it.
you
Go to the view. Go to the view. On the top right. On the top right. Yeah. Gallery, multi-speaker, anything. Multi-speaker. Multi-speaker. Yeah.
okay. Yeah, so we have few questions.
Yeah, sure.
Okay. Yicheng, you have any questions? No?
Not
Does it? No. Yeah, you can go.
Yes, start from you. Yeah, if you have a question, go.
Okay.
Yeah.
So, yeah, it was a nice presentation.
Okay, thanks.
So few questions I have. So in the fusion blocks, whenever you're talking about like kind of oh, okay. So whenever you're talking about something where you're fusing
Better system.
cross attention or the self attention, did you use any sort of layer or some sort of patch or something like normalization layers over there?
Yeah, I use normalization. So before you, so you get the feature representations of audio and visual modalities. Before you feed that to the fusion block, we normalize the features. So I used L2 normalization for
L2?
both audio and visual before feeding that, and then I do fusion on the normalized features.
You, okay. Yeah.
Yeah, it's a good question.
Huh? Dimensionality alignment. No.
So, Praveen, I have a
No.
few questions.
Dimensional
So-
Yeah,
alignment
sure.
is
So we are working on some project regarding audio processing as well. So you have used
Okay.
vocal spectrogram. So typically,
Okay.
is it better to use a spectrogram rather than just using some like a convolution neural network on low data? For example, if it is like an audio,
Hmm.
do typically is it better to use a spectrogram as an input?
Okay, so if I understand your question is it better to use spectrograms or like 1D signal as it is?
Yeah,
Like, is that
exactly.
your question?
Yes.
Yeah, yeah. Like there are advantages and disadvantages in both, but it mostly depends on uh, like on your application and what kind of information that you are like. What is the task that you are trying to achieve? Typically, if you see in literature for emotion recognition, spectrograms seems to carry significant emotion relevant information.
Oh, I
Uh,
see.
a- and another advantage with that is like uh, uh, like it is easy to like once you have the a spectrogram, you can think of it as an image, right? So then it is easy for you to process it, like an image. Like you can use like resonant 18 or some 2D CNN models, and so like in fact like one of the recent works which we submitted to NeurIPS workshop is based on vision transformers. So we use vision transformers to extract the feature representations for both face and voice. So the idea is, since you have this spectrogram, which is a 2D image, like you can think of it as a 2D image, you can feed that into the vision transformer and do further processing. So I think it depends on the application. For example, like I also worked on speaker verification. So in speaker verification, people mostly use 1D signal. Like you won't find many papers that use spectrogram for speaker verification.
Yeah, I think,
So
that makes sense.
I
Because
think it depends on the application. Yeah.
yeah, because I think not only 2D domain as an input, but also spectrogram helps to get some frequency on the, information.
Yeah.
So
Yeah.
depending on the application, I think we can try both of them. But yeah, that's clear. And I have a question about your skip connection method in the
Okay.
first page. So, so as an activation function, you have used a TANH, and just out
Yeah.
of curiosity, does different type of activation function impact on the final outcome?
Yeah.
Like for example, does it impact like a large on what if it does, like what other, like as an ablation studies, like what other activation function rather than like TANH has been used? Just because I was like wondered what other.
Yeah, TANH. I mean, like one thing to remember here is, like your labels are between -1 to 1.
Uh-huh.
Okay,
Oh,
and if you
okay.
look at the output of TANH, that is also -1 to 1. It's not
Okay,
from
that
0 to 1.
yeah. Okay.
So that's the reason we used TANH.
Okay. So this is more like, could it be tailored to the data set you are working on?
Yeah,
And like,
yeah. I mean, there is no rigid rule as such. It depends on the application and data set that you are working on, and we can play around.
and one last simple question. So I was working on different type of multimodal learning, but in general, all of your work was working on kind of like a concatenation from different modality. For example, like have you
Mhm.
have thought about like stacking those features extracted from different modality, for example? Because you typically from different modality, you just concatenate it, right, all together in your fusion
Mhm.
plot.
Mhm.
But I was wondering, like, have you thought about like stacking those features rather than concatenation?
Okay, you mean stacking the features? Uh, yeah, I did that. I did some experiments with stacking also, but not on the fusion side. Uh, like I did some experiments by trying with different backbones
Okay.
for individual modalities and then stacking those features.
Mhm. Okay.
So, uh, but I didn't try stacking on the fused features. On yeah, I didn't try. I didn't try stacking. Probably, I'm not sure. Maybe we can try that.
Okay. Okay.
And
Yeah. I mean,
why it's different, like why stacking will be, like why it's gonna be maybe different results.
No, in concatenation, I think you concatenate the features, right? But in stacking, you uh, you assume that as individual features, right? Like if I'm right in stacking, basically you have these two features. Instead of concatenating, you assume these as separate features, and
Okay, I
then
see.
you do the prediction, and then finally you try to do some sort of aggregation or something like that.
Okay, I see the point. Okay.
So usually stacking is done when you have similar features coming from the same modality. That's where you use stacking. It's beneficial. Usually we use stacking to somehow make it easy to compute. Like you sometimes you're gonna find, especially when you're dealing with attention models, that it takes a lot of memory. At that time you split the tensor and you stack them. That's where the stacking is really beneficial. But concatenation is a good when you want to keep that temporal thing. That something, for example, in LLM, what we say is like query
Yeah, to
followed by
retain the temper. Yeah.
first thing is system and then user. So system, you are a good agent, you are this, you are a specific doctor, blah blah blah. My question is blah blah blah. So that question concatenated with this question is
Okay,
like getting entire temporal. Stacking is
I
gonna
see.
mess it up. Okay.
and and if you
But I
see the
think I see the point of Dr. Lee here, because in facial emotional recognition, somehow I was gonna ask this a question, like when you do cross attention and concatenation, when do you fusion, let's say someone was smiling or laughing in the first second of the video and then is, I don't know, crying after maybe 3 seconds. When you concatenate, doesn't like impact or do cross attention, does that, how you deal with this situation, doesn't impact the prediction or the extracting of the feature?
Yeah. So as I mentioned before, like one of the important thing is to properly synchronize the modalities. Which means that you cannot do concatenation. For example, you get an audio feature for the first second. You cannot
Mm-hmm.
do concatenation with the third second of visual feature.
I
The
see. Okay.
timestamps, the timestamps has to be well synchronized. Like otherwise, it will mess up everything. Okay,
Okay.
so that is important. And another reason for me to use concatenation here is like I want to uh, uh, like I don't want to distort the features. Like when I compute cross correlation of the feature representations of individual modalities across the joint feature representation, I don't want to distort the features. I want to retain the features as it is and still do the cross correlation across the individual modality as well as the multimodal representations. But if you do some sort of stacking or like some other thing, you might distort the original features. Probably, like we can try that, but my intention is to retain the features as it is, like without distorting that, and then do the cross correlation. So that's the reason that
Yeah,
size
I see your point. Like, because what I was thinking is you are trying a voice mode audio with a picture, but when you do cross attention, maybe the voice in the first second and the picture on the, they will still be uh, crossed attention together in the operation with the picture of the fifth second, for example. Am I right?
yeah.
Yeah.
Yeah, right. So in a cross attention, we try to do the cross correlation like across multiple timestamps. So
I see.
basically what we do that, given the video sequence, you divide the video sequence, let's say uh, into let's say something like 8 segments. Okay,
Okay.
now you
Okay.
now you have 8 segments which corresponds to the feature presentations of consecutive video clips of face, and similarly we you get the 8 feature representations of voice,
Oh, yeah.
which is
Okay.
consecutive clips. And now you try to compute the cross correlation of each feature representation